All right, ladies and gentlemen, this class recording has started. So, this unit we talk about is mechanics, and mechanics is the study of motion. And the first thing that we have to do in order to study motion is describe motion, right? That's the first step in the scientific process. We make observations. After we make observations, then we do what? As far as a general, not necessarily the scientific method, but in terms of like what is science. Go ahead, Shane. Yes, we do experiments, we find more information, but what do we do once we get all this information? What do we look for? Patterns, trends, right? Things that keep happening over and over again. So the first part of this unit, we define a bunch of things. Distance, displacement, speed, velocity, acceleration. But the second part of this unit, now we start looking at patterns. If something is accelerating, what does that do to the velocity? And then what does that ultimately do to the displacement of that object? So that's what we're going to do this week, is start exploring some of those patterns. What happens when this changes, and how does it affect the other things that we describe motion with? Okay? So we're going to start off on the first page, up at the top, with non-accelerated motion. What's another way that we can describe non-accelerated motion? Constant velocity, right? If something has a constant velocity, what two things have to be true? If something has a constant velocity...
Constant acceleration?
Not necessarily.
I mean acceleration.
If it's constant velocity, what does the acceleration have to be? Zero. All right? If something has a constant velocity, its acceleration is zero, right? Does that make sense? Even graphically or conceptually? Yes, no, maybe. Okay. Well, what's our definition of acceleration? Speeding up, slowing down, or changing direction, or more generally, a change in velocity. If we have something that has a constant velocity, what does that mean about the velocity? It's constant. It's not changing, right? Okay? So if something is going to have a constant velocity, a non-changing velocity, what has to be true about it? Acceleration is zero. Good. If we were looking at it, what would we see? On a graph, maybe. If we were looking at the object, what would we see? Same speed, same direction, right? That's a constant velocity, yes? Does that make sense? Okay. All right. So let's take a look at this picture, and let's start piecing some of those things together. First, if this is non-accelerated motion, that means it has constant velocity, and that means that the acceleration of this object is what? Zero, right? Or to be consistent with what we're going to do a little bit later in class, 0 meters per second for every 1 second, right? That's our unit of acceleration, right? Meters per second, yes? To be consistent with what we're doing later on in class, I'm going to start it like this, okay? All right, so picture, it says, the sketch shows a ball rolling at a constant velocity along a level floor. The ball rolls from the first position shown to the second in 1 second. Now, this this picture doesn't show the ball at the second position, but from here to here, that takes 1 second for the ball to roll that far. Okay? Good so far with sort of the setup of this problem? Okay. All right, it says these two positions are 1 meter apart. Sorry, 1 second, 1 meter apart. Okay? So if the ball travels 1 meter, and it takes 1 second to do that, what is the ball's velocity? 1 meter per second, right? It goes 1 meter for every second that goes by. Fair enough? Okay. So next, it says, sketch the ball at successive 1 second intervals all the way to the wall. All right? So I'm going to start off, and I'm going to draw a line that is this pink color right here. And I'm going to start it here, and I'm going to take it there. Okay? You'll see why in a second. All right. If the acceleration is 0, if it took 1 second to go 1 meter, in the next second, how far is the ball going to go? Well, in 1 more meter in 1 more second, right? Yes? Okay. So we can take this pink line and move it over here, and then draw the ball again, and it would be there. Right? In the next second, how far is it going to go? 1 meter. Right? So just as like kind of a ruler, right? I'm going to take this, I'm going to move it over here, and then I'm going to draw the ball right there. 1 second after that, how far is it going to go? 1 meter. Right? And then finally, 1 second after that, how far is it going to go? 1 meter again. Okay? Come on. There we go. And we end up at the wall. Okay? Yes? So these pictures all represent 1 second worth of time. It's kind of like a time-lapse picture, you know? Or have you ever seen like Lego animation? Yes, right? Where you move the Lego a little bit and take another picture and move the Lego another picture, right? You know? This is all 1 second in time. So from here to here was 1 second, and then here to here was 1 second, here to here was 1 second. Every time a ball shows up on this picture, that represents 1 second of time passing. Okay? That's going to be important later on as we start looking at these things a little more. Okay? All right, so question A. Did we draw the successive ball positions evenly spaced, further apart, or closer together? Evenly spaced here. All right? Why? What's constant in this example? Velocity. And velocity is a relationship between what? Position and time, right? How far did we go? How long did it take us to go there? If the velocity is constant, we keep going the same position or the same distance every time, right? When the ball reaches the wall, what is its speed? 1 meter per second. It's still traveling at 1 meter per second, but how long did it take us to get there? 5 seconds to get there, right? Now in this case, there are 6 pictures, right? Because this right here, this is time equals 0. That's like the very starting position, right? I know this seems kind of simplistic. I'm just going through this because we're going to use this setup later on to explain some things. So I want you to understand this picture for when we move on. Right? I'm not trying to belabor this point of constant velocity. I think all of you could figure it out, but for just this sake right here. Okay. All right. Good so far. Good. Okay. Here, do we need to go through these? Do we need to go through these calculations? No. Right? So here, right, speed is a relationship between 2 things, right? Speed is a relationship between distance and time. Yes? Right? So if we know distance and time, we can figure out the speed. Just like there. Right? So for the Greyhound, they gave us how far it took and how far it went, how long it took us to get there, right? For the Gazelle, it gave us a distance and a speed, and it wants us to figure out the time. I can rearrange this equation to look like this. Everyone see how I did that real quick? Okay. So in this case here, if I know my distance is 1 kilometer, and I know that's 100 kilometers per hour, the time is going to be 1/100th of an hour, which we did the calculation earlier in class today is 36 seconds. And then finally, for the turtle, they gave us a time and a speed. We could also rearrange this equation to look like this. Yes? S times t is equal to d, right? And if you do that, right, you end up with 30 seconds. Good? Yeah? Okay. That's pretty boring. That's pretty simple. Nothing changes. Let's talk about this drag racing car. Okay? So here this picture is showing us the position of the drag racing car at consecutive seconds after it hit the gas and started the brakes. Okay? What are we seeing about how far this car travels from 0 to 1, 1 to 2, and 2 to 3? In each consecutive second, how far is the car going? It's going farther each second, right? If it goes farther, but we're still talking about 1 second, what does that mean is happening to this race car? Yes, it is accelerating, but more specifically, it's speeding up, right? If it's going farther, but the time is the same, it has to be going faster, right? So whereas in this picture, when we draw the position of the rolling ball, they all end up being spaced evenly. For this one, because that spacing is increasing, that's indicating to us that that object is speeding up. Okay? Here's another example. Guy riding his bicycle. Based on the positions, based on the locations of this guy and his bicycle, what can we say? He's speeding up. His velocity is increasing. All right? Now, here let's start getting a little bit more analytical, a little bit more making sure we understand things. If this object is speeding up, that means that it is accelerated motion. Okay? So, we said that accelerated motion could mean 3 things, right? It means it could mean the object is doing what? Speeding up, slowing down, or changing directions. We've already established this object is speeding up. Okay? What is the acceleration of this object? Talk to the person next to you. What is the acceleration of this object? All right, so you'll see that all of the examples that I do in this section, I'm going to basically start with the same thing, and that's write the acceleration up on the board. And I'm always going to write it in that format, because that's what acceleration tells us, right? Meters per second per second. How much does the velocity change every second? Here, it was 0 meters per second, right? Because the velocity was always 1. How much does the velocity change for every second that goes by? It goes 2 meters per second faster for every 1 second that goes by. So the acceleration of this object is what? 2 meters per second, or 2 meters per second squared. Okay? Good there? All right. Terminology. What would we call those things that I just highlighted? Something more specific. So, those numbers that I highlighted right there are instantaneous velocities. Does that make sense? Yeah. Right? We said that instantaneous means what? Like one instant time, right? One instant in time. So this is the velocity of the bicycle at this moment. This is the velocity of the bicycle at this moment. This is the velocity of the bicycle at this moment, right? How much does the instantaneous velocity change each second? 2 meters per second. Or if we wanted to make a general pattern out of that, right? How much does the instantaneous velocity change each second? In this case, yes, because we've said that that's the what in this problem. What is 2 meters per second in this problem? The acceleration, right? So the instantaneous velocity will change by some value equal to the acceleration. Does that make sense? If we know what the acceleration is, we can predict what the instantaneous velocity will be after 7 seconds, or after 10 seconds, or after 50 seconds. If the acceleration remains 2 meters per second squared, what will happen to the velocity every second that goes by? It'll increase by how much? By 2. All right? Does that make sense? You okay with that? All right. That's our first pattern that we're going to talk about. The change in velocity related to the acceleration. Now, what we do in science a lot is come up with this pattern and then try to come up with a way to represent that pattern. A lot of times, representing that pattern comes in the form of a mathematical equation. Okay? The mathematical equation that represents that pattern looks like this. Okay? So does that make sense? It is up on that board. Yep, it's up on that board, right? We won't get through all those equations, but it is up on that board. Right? No, that got made at Cedar Point. So a couple of my physics students, Tia, Ken's, Kelton M, they got it made in Frontierland when we went there for physics the one day. And they came back to the bus and they're like, here, we got this made for you. So, yeah, we got to Cedar Point in physics class. So, not for you guys. So, not yet. Yeah. I mean, it's a field trip. You know, you have to like do some work while you're there. So, you do get to ride rides, yes. So. All right, so, right? Yes, you have to calculate things like that. All right, so this pattern, right? VF is going to stand for what? Final velocity. VI stands for initial velocity. A is acceleration, and T is time, right? So we can figure out how fast something is going at the end of its trip if we know how fast it was going at the beginning of its trip, what its acceleration is, and how long that trip takes. If we talk about neat 1 second intervals, it just goes up by the acceleration. but we could figure out how fast this bicycle rider was going at like 4.7 seconds if we wanted to, knowing this relationship. Okay? All right, so that's the first relationship. Tomorrow, we'll start pulling in some displacement and some distance traveled stuff into this discussion as well. Okay? Don't lose that packet. We're going to use it all week, so...